Good morning, everyone. My name is Soham. I'm studying mechanical engineering at BITS Pilani. My project is on passive sonar deployment as well, but my target is the vulnerability assessment. Essentially, the problem that we're trying to solve is finding zones where we can hide from our target. But the project assumes that we don't know where our target is either. So we essentially have two regions. So what it hopes to solve is from a target region, we can map out into our own region positions that are advantageous for us. That means that we can do surveillance on them, but we are hidden from them. That is where the vulnerability assessment comes into play. And this will be working on detection asymmetry. What detection asymmetry essentially means is, as Tulika explained, signal excess is how we increase our probability of detection. So, in positions where our signal excess is lesser than zero, that would mean that there is more noise, and where it is greater, that and to what extent, that would imply that there is a possible signal there. But detection asymmetry says that there will be variables. Actually, I should have added that earlier. Yes. So these variables. So, for example, transmission loss will be the same between 2 points, but the asymmetry comes into part that source level, detection threshold, and array gain. These are three variables that will be dependent on the type of vessel being used. So that can change your signal access and the target signal access. So this is what the whole project revolves around. I could just go back. So before I get into it, I'll discuss some opportunities and relevance. So of course, there is naval offense and defense, and it's a essential tool for anti-submarine warfare. Of course, there are existing tools, but we are trying to work on our own as well. Emerging need as India is shifting from a buyer's navy to a builder's navy in the past decade. So building and working on indigenous tools is necessary, and it may not be a stretch to say that there is some blue economic value to such a project as well, because it is essentially surveillance. So we can take it a step back, and instead of hiding from the target, we will get a map of positions that we can surveil as well. So if there is a high priority asset that we are deploying, we can assess it. So the source level, the detectivity index, or the array gain, and the detection threshold are the three variables that my project will be calculating in-house. And the transmission loss and noise levels are something that the project is going to take in as outside inputs. So for source level, I have chosen Jomopan's Echo, which is a source level model. So why I've chosen this is because it can work on readily available AIS data. So for a proof of concept or for actual value calculation, this is very good. Receiver gain now, array gain usually is calculated assuming anisotropic noise, because ocean noise is anisotropic. But for our first prototype, we have assumed that there is directivity index. That means there is isotropic noise for our receivers. Now, detection threshold is we are basically going to simulate receiver operating curves using statistics. That is how we are going to calculate detection threshold, which will take in probability of detection and probability of false alarm that a operator is willing to take. We'll discuss this further. So yeah, as I said, these are the three things that we'll be calculating in house. Noise levels are something we'll be taking as an input, and so is the transmission loss. So as I said, detection threshold, we are simulating ROC curves. We are taking the probability of detection, probability of false alarm, the bandwidth, and the integration time that an operator is satisfied with. Um, so this was something that we attempted to do to simulate a noise space, you could say. For example, if this was our receiver, we tried to simulate anisotropic noise, but we're still working on that, so it's not part of the first prototype. So detection threshold, once again, we go over it quickly. You can see wherever there is a high probability of detection, it says 0.9, and a very low probability of false alarm, which is 10 to the power minus 4. You can see that the detection threshold is positive. What this essentially means in this equation is that it reduces your signal excess. So that means it's more accurate, but it is less likely to occur. And in cases where we are relaxing our values at the same at the same bandwidth and integration time, we can get a negative detection threshold, which is 0.5 probability of detection and very high probability of false alarm as well. What this would mean is that it will give a lot of false alarms as well. But what this slide is trying to show is that the model can, or the script that we have written can account for both of these cases. Um, Once again, we are going to use the directivity index for our prototype. We are going to use simple equations from Urich's textbook, Principles of Underwater Sound. And for source level, we are using Jumopan's Echo using AIS data. And for vessels or types of vessels that we don't have AIS data for, of course, we don't have data for every vessel that we are going to target or the target is going to be. So we have taken these values from Xavier Lawton's textbook, which are for your source level itself. Now, once again, it some key advantages and features. It is multi-platform because we can take in different vessels as our source level. Depending on that, the script that we have written can account for these variabilities. So it is multi-platform and risk-based, as I showed in the detection threshold. Depending on what kind of risk the operator is satisfied with, what their vessel's capabilities is to detect these and to act upon these, they can choose their own detection threshold. So far, what we've been able to achieve is a complete backend of the detection threshold, source level, and directivity index, which is the R again. And we have a script that can take in these values and generate a final comma separated value output that can then further be plotted into our advantageous zones in our own region and in the target region. But one thing that such a binary output would be missing out on is sensitivity analysis, which is some of the next steps, because your increase from the signal excess or closeness to the signal excess is also important. So if your signal excess is 0, 1 decibel, 2 decibels, 15 decibels, it brings out variability and sensitivity that we have not accounted for over here. And of course, one of the other steps could be to change your directivity index into the realistic array gain that we are trying to do. Thank you.